Hey, McFarland, can you unmute your mic, please?
Sorry about that. I did not realize I was muted.
Thank you.
Okay, yep. Okay. All right. I'm looking in the answer, the solutions manual, so I don't know exactly how the question was set up, but I'll just set it up like this. Okay, so looking at this setup, what would you expect the product to be? What's that? It's not going to be a ketone. It's going to be an aldehyde, right? This is an example of an oxidation of an alcohol, right? And if you remember, certain types of alcohols will oxidize to certain types of compounds with certain types of oxidizing agents, right? So first thing you have to recognize here is that this is a primary alcohol, right? The OH is attached to a primary carbon. And then you have to remember, well, primary alcohols, they can do one of two things. If you have a strong oxidizing agent, they can oxidize to a carboxylic acid. If you have a weak oxidizing agent, they oxidize to an aldehyde. And that's what this one does. Right? PCC is the go-to weak oxidizer. In fact, I think it's the only one that we've talked about with regard to alcohols. So that can sort of help guide you. Does that help?
Well, in the book it has CHO, so that's how I've written the answer too. But I mean, I guess it just messes me up because it has the double bond.
Yeah. Let me see. I forgot there's a double bond here, but it really is important. So in the answer key, it has it written like this. This means exactly the same as this, right? It's just a what they did here was they sort of mixed condensed structure right here with skeletal structure. So what you have to be able to do is look at this and sort of figure out what the skeletal structure would be if you want to convert it. So basically you look at it, this carbon already has one bond, right? So how many more bonds could it make? You guys know this. How many bonds does carbon like to make? 4. It's got 1 already, so it can make 3 more, right? So you have to figure out how the 3 bonds are distributed amongst hydrogen and oxygen. You know carbon can only make 1 bond to a hydrogen, so that means it must have a double bond for the oxygen. So it's playing around with those bonding rules that we went over in chapter 1. Does that help?
Mm-hmm. Do you have an example of one like a strong metal oxidizer?
Sure. Let's say we took something like this. Sometimes I kind of like to draw these just because they're tricky looking. What type of alcohol do we have? It's primary. Kind of looks like a secondary, but it's not. It's primary. All right, so if you wanted to make this into carboxylic acid, first of all, the acid would look like that. All right. Since we're going from 1 bond to oxygen all the way up to 3 bonds, that means we need a strong oxidizer. All right. And there's several different ones that you can use. They're listed in your book. The ones that we've been doing primarily as examples Potassium dichromate or sodium dichromate. So like K2CR2O7, Na2 CR2O7. You could also use, I think, potassium permanganate, KMnO4. Yeah, so there's several of them that you can use, usually in conjunction with sulfuric acid and water. Right? So you add a strong oxidizer like this, you get the acid. If we were to add instead PCC, we would only oxidize one level to 2 bonds to oxygen and give us an aldehyde. Does that answer your question? What's that? Yeah, it's there. I just didn't, I drew it at less of a slant than I did over here, or less of a severe angle. So it looks kind of wonky.
I have a question on
Okay. Do you want to just project it?
Yeah.
That might be the easiest thing.
Yeah, I can just airplay.
Yeah, just use AirPlay. 002 is the room.
You're doing that, I'll try to work with it.
I can never remember which lights do what. This one? All right, so draw the major products for the reaction shown. So I have this. 1, 2, 3. I'm just going to put a zigzag in it so it's a little bit easier to see. Okay. So a couple of things. Sometimes you'll see the reaction setups are a little bit different in sapling. Just to clarify what these are, O3 is ozone. We've talked about that. CH2Cl2, that is dichloromethane. That's a common solvent that's used. So if you see dichloromethane, it's probably just being used as a solvent, not as a reagent. Normally, solvents go below the arrow, but since we're doing a multi-step reaction, they had to sort of fit it in somewhere else. They're working the reaction at negative 78 degrees Celsius. Right? Then in the second step, they added zinc and either water or the HOAC. Just FYI. Too many letters. That's acetic acid. AC stands for an acetyl group, which is this. So, by the way, anytime if you run into any of these little abbreviations and stuff that maybe you haven't seen before, feel free to ask me what they are. I'm happy to fill you in. Yes, ma'am.
What did you say HOAC?
Acetic acid, which is, and this is the structure of acetic acid right here. All right. So for your purposes, what you're really interested in here, as far as reagents, are going to be the ozone and then the zinc and water system. Okay. So you have ozone, zinc and water, and then you have a terminal alkyne here. Right? What type of reaction is this? Do y'all remember? What type of reaction is this that you're using ozone in? Oxidative cleavage. It's a type of oxidative cleavage called ozonolysis, right? All right, so the term oxidative cleavage tells you that you have to cleave something, right? So you're going to cleave this molecule into two pieces. Where do we do it? Where do we have the cleavage? Yeah. Triple bond, you mean? Yeah. Yeah, right in the middle of this triple bond. Right, so you're going to divide this thing into a 1 carbon fragment and then this bigger piece over here, right? So this is a case where you have to use the M word, memorization a little bit, right? When you cleave a terminal alkyne, what products do you always get? The 1 carbon fragment. I'm going to sort of swing the arrow down here. The 1 carbon fragment is going to be carbon dioxide, CO2. Right? What does the other fragment turn into? It turns into a carboxylic acid. So this carbon right here okay, this is way too low. Come on, drop it. Now contains a carboxylic acid group. So yeah, anytime you see an oxidative cleavage reaction, as far as the site, it's really simple. Target either the triple bond or the double bond, depending on the situation, and slice it right in the middle. The trick is remembering the types of functional groups that you get afterwards. And that's where you have to do a little bit of memorization. Does that answer your question? Does that help? You're gonna check to see if this works, aren't you? Let's see how it turns out, because I could see there has been a quirk in previous saplings where this might not be the full answer, but we'll see how it turns out. We wait with bated breath. I keep thinking this is like a bond that you draw, but it's actually just a mark on the screen. What's that?
CO2.
Nope, there's no carbon. So you'll want a something like that. There you go. Yay! All right. All right. Other questions?
For hydroboration of a terminal alkyne, you'll get ethanol with aldehyde, right? For synthesis purposes, you need to use something else if you want aldehyde, because will those be we get a mix of those?
For all intents and purposes, when you have that equilibrium, for all intents and purposes, it's basically all aldehyde. I mean, there's like just a minuscule amount of enol there, but not enough to, make it to really have a negative impact on your yield. So yeah, you're safe doing that. Yeah.
So for the oxidative cleavage question, would the reagents vary based if it was an alkene or alkyne?
For alkenes, you need ozone and then a zinc and water system, or zinc and acetic acid, as we saw there. For alkynes, you may or may not have zinc. Zinc's not always necessary, but sometimes it's used.
So if we were like to just use O3 and H2O for an alkyne,
That'd be fine.
as long as we have the right product.
Yep.
Okay.
Did y'all get my message about the synthesis problems on the test? Okay, good.
Is it a
I'm getting
front-
soft in
front
my
and
old
back?
age or something. What's
Is it
that?
a front and back issue?
Yeah, you can use front and back.
Do you want to do the ozone for internal?
For an internal alkyne? Yeah, sure. I get creative. Add a bunch of stuff to distract you that means nothing. Like that cyclopropylene. Okay, so this is an internal alkyne. So oxidative cleavage or ozonolysis of internal alkynes is very similar to that of terminal alkynes. The big difference is that you're not going to end up with a one carbon fragment. So do you think carbon dioxide is going to be a product? No, because you have more than one carbon, can't be carbon dioxide. So what do you think we get? Well, terminal alkynes, the other product besides CO2 was what? Carboxylic acid. So what do you think we're going to get here?
Two.
You're going to get two of them. Yeah. In a case like this, both of these carbons are oxidized into acid groups. So you get that carboxylic acid. And then you also get this one. And there's really nothing else I can say about it. Here you go. More questions? Y'all want to sit there and think of something too, that's fine. You don't have to have them out. No free radicals on this. They're on the next one.
Did you do a oxidation
For alkene? Yeah. Okay, so oxidative cleavage of an alkene. All right. First of all, just like we saw with alkynes, your target is going to be that multiple bond. So you're going to cut it right into the middle. All right. Now, whenever you do an ozonolysis of an alkene, again, we end up with certain types of products. What types of products do we typically end up with for alkenes? Aldehydes and or ketones, right? So it's not going to be acids in this case. Acids you only get with alkynes, right? So basically what happens is whenever you cleave this, this carbon is going to turn into a carbonyl, C double bond O. Same thing for this, right? So for the left fragment, since you're on the end right there, you form an aldehyde, right? You just literally simply replaced this carbon double bond with the carbon oxygen double bond. The H has always been there, we just didn't draw it in, all right? You do the same thing over here, except you notice this carbon has two R groups. It has an ethyl and a methyl. So it's a ketone. So in this particular example, we get one aldehyde and one ketone. Sometimes you get this, sometimes you get two aldehydes, sometimes you get two ketones. Just depends on the structure of the molecule. Okay? Does that make sense? What about this one? We didn't go over one like this. I think you can figure it out. What if it's a marine? Well, what do you think?
Got the double bond, and each carbon attached to the double bond gets double bond.
Yeah, you treat it, yeah, exactly. You treat it just the same as before. The only difference is when you split this here, the two fragments are still connected, right? So you end up still with only one molecule. 1, 2, 3, 4, 5, 6. But it's linear now. It's not a.
I think we're missing a carbon.
Am I?
The one that's taking off the second.
Oh, no. Thank you. Yeah, sometimes people get a little freaked out about seeing this with rings. You treat it exactly the same though. Just, you have one molecule with two functional groups instead of two molecules, each with one. More questions? I'll make myself comfortable. Feeling good, feeling confident. That's not good. Yes.
Why are there two oxygens?
What's that?
Why are there two oxygens?
Why are there two oxygens? Because when you cleave this double bond, remember each carbon that was involved in the double bond turns into a carbonyl, right? And so oxygen is an inherent part of a carbonyl. It just looks a lot different than doing something like, this, right? Because you're used to seeing like this split up into two different fragments, each with one, right? So it's really the same thing, it just looks kind of weird. Yeah, each carbon that was in your double bond gets an oxygen. Yes, ma'am.
Are there going to be any questions like this example that has maybe like 2 double bonds? So I have some examples.
There could be. Let's see. Let's do this one. Okay. So you might run into, yeah, it's certainly possible. I didn't think, Christy, were you talking about a cyclic one or just a, like
Yeah,
a cyclic one? Okay. I didn't even think about that properly. All right. Simply put, whenever you have one of these oxidative cleavages, that ozone is not picky. It will go after any carbon-carbon double bond, in this case, or in the other case, carbon-carbon triple bond that's available. So in one like this, you're going to cleave right here, and you're going to cleave right there as well. All right? So it's literally like you're taking a pair of scissors, snipping here, snipping here. So if you look at this, that sort of cleaves off this big fragment right here that has 1, 2 carbons. All right? What do you think this 2 carbon fragment would look like after it's oxidized? Follow the rules that we've been given. Yeah. This used to be part of a carbon-carbon double bond. This used to be part of a carbon-carbon double bond. They both get carbonyls. So this is a dialdehyde. It's got 2 aldehyde groups. Same thing over here, right? This is a 1, 2, 3 carbon fragment. Each of the end carbons used to be in double bonds. So they're both going to be aldehyde groups as well. So yeah, if you encounter one like this, first of all, carefully mark, carefully decide where you're going to be snipping with your imaginary scissors, and then you figure out the appropriate fragments you're going to have with the appropriate number of carbons, and then figure out which carbons get your carbonyl. If it used to be in the double bond, it gets a carbonyl. I have to say, I'm impressed you guys are asking some pretty good questions. A lot of times I do this and like people are literally just staring at me for like the whole time. Yeah.
I'm just confused about like the setup of the second one. Are there 3 carbons? Because I'm
Over here?
Yeah.
Yeah, there's 3. 1,
Oh.
2, 3.
Oh.
Yep. Yeah. So like if you're trying, if you want to like label them, and some people do this just to keep track.
Okay.
Any other questions? For you Zoomers out there, I'm giving the class a minute or two to come up with something. I feel like an entertainer. I have to fill in dead air. I should have like a comedy routine. Do our Zoomers have any questions? Our Zoomers have any questions? Feel free to put them in the chat. Or you can ask me while I'm staring at the screen. I'm sorry? Come up with a synthesis to work, okay? Any particular type or just surprise you? All right, give me a second. Let me open up my e-textbook here and see if I can find any good examples. All right, let's see what we got. I gotta find a somewhat tough one. Let's see. All right, let's try this one. Sort of modifying one I saw online. So give me a second to make sure it's. All right, give me a second here. Make sure this works. Okay, I think this works. You can do this in 4 steps. Yes, ma'am.
On the test, are you going to tell us how many steps it's going to take, or are you just going to?
Am I going to tell? Oh, I didn't when I printed it out. I might tell you like, the only danger in doing that is sometimes people think, okay, it's got to be 4 steps.
Mm-hmm.
And like I said, there's more than one correct pathway sometimes. So I'll just have to make sure to emphasize it's the minimum number of steps. But yeah, I'll do that. All right, the minimum, as far as I can tell, just off the top of my head, for this one would be 4 steps. And this one's not, this one's fairly tough, I think. Work on it for a couple minutes. See if you can come up with any of the steps, any or all. We'll make sure to come back to it with enough time to finish it before the period ends. Fun fact with this one, once we finish the radical chapter, you'll know how to do this in 2 steps. But you don't know that, you don't have that knowledge yet, so.
Oh my gosh. 'Cause I think I have an idea in my head, but I don't know how to do it.
All right, I know you guys haven't had much time to work on this, but just to make sure we have enough time to finish going over it, let's go ahead and talk about it here. So, did y'all come up with anything? Any ideas? Yes. All right. All right. So first, you're going to make an alkene. Is that right? All right. How do you want to do that? That works just fine here. Honestly, you could do it either way in this particular case, since there's no cis trans for us to worry about. That will give us an alkene. And then what do you want to do? All right. So you can do hydroboration oxidation. That's a 2-step process in and of itself. And if you guys remember, when you do hydroboration oxidation of an alkene, that gives you an alcohol. Specifically, it gives you alcohol in a in an anti-Markovnikov addition. In other words, specifically, that OH is going to go on that end carbon. If you did a hydration instead, the OH would have gone in the middle. All right? This is all correct. So, yeah, go ahead. Sorry. HBr works fine. Yeah. The last thing is to convert that alcohol into BR. That's going to be stuff from last semester. So HBr works just fine. You could have also used PBr3. So yeah, very good. I encourage you, and this is one thing a lot of people don't do sometimes. I give you a whole lot of time. I give you a whole lab period. It's not uncommon for people to kind of work on this for a little bit, get frustrated, and then just kind of move on. Think about it. These things take a little time. Get the little clues, put them together. Yes? Over here? Yeah, you could have absolutely used PBr3 instead. Yeah, that works. So there's an example of a couple of different ways that you can do it. All right. Any questions on the synthesis example we just did? All right, we're almost out of time. Does anybody have any quick questions they want to ask before the period ends? All right, if not, I will be in my office today until the lab period. So basically from now until noon. So if at any point y'all want to come by and ask me something, I'll be there. So feel free to come on by. All right, that's all I got for you. So I'll see y'all later.